In this video, we're going to demonstrate how to do a battery starting system and charging system test on a car using a lab scope. Now, I'm assuming with this video that you already know how to use your lab scope. If you don't, if you need more practice, I'll put a link in the corner of the video to my video that shows how to use a lab scope or how to set it up for the first time. So what we're going to do here is set this up to measure battery voltage and battery current while we start the car and let it idle for 5 minutes. Now, this is a very simple test, but there's a lot of really valuable information that we can gather from this waveform that we're going to collect. So to set this up, I've got channel A set up with my voltage probe, so I've got it on the battery, positive and negative terminals of the battery. Channel B, I have my current probe. It's already set up and I've zeroed it, and the scale is up to 600 amps. Now, here's a really important part in doing this. I need to make sure that I get around all of the cables. It doesn't matter whether I put it on the positive or the negative, but if there are more than one cable here, I need to get around all of them, observing the polarity of the current probe here. This arrow always points the direction of conventional current flow, which means it's flowing away from positive or toward negative. So if I'm putting it on the positive cable here, I want to get around both cables with the arrow pointing away from the battery, like this. Now we're going to start the car and let it idle for 5 minutes. Okay, we fast forwarded through the 5 minutes now. We've now recorded our data for 5 minutes. Now, there's one more thing that I want to do before I disconnect the scope from the car, and this is optional, but there's something that I can do that will help me to get even more information about the charging system. So I'm going to come over to the car, and I'm going to move the current probe over to the output wire on the alternator. This is the big cable, the B terminal of the alternator. Observing the polarity, so this should be pointing away from the alternator. Now what I'm going to do is I'm going to go into the car and I'm going to turn on all of the big electrical loads of the vehicle. So the high beam headlights, the rear defroster, the blower motor, and the air conditioner, just some of the big loads. And then I'm going to rev the engine up to about 1500 RPM, and so we can see what the alternator and charging system is doing under a load. And that concludes our data capturing, so we can stop this now and we'll go analyze our waveform. Okay, so now let's sit down and look at this waveform for a minute. On channel A, the blue channel, we captured battery voltage, and on channel B, we captured battery current. There's a lot of information on this waveform, and we can use this to determine the health of the battery, of the starting system, and of the charging system. So let's start out by looking at the battery. There are a few things that we can learn from the battery. Let's zoom in here on this section, but first I want you to see that when we started the car right here, current rose. It rose up to about 900 or almost 1,000 amps was drawn from that battery during initial starting, and during that time the battery voltage was pulled low. So we've done a load test on the battery. So I want to take a look at this section right here. Bring my pointer down and I want to look and see what the state of charge of the battery was. It was at 12.79, almost 12.8 volts before we started, which indicates that this battery was 100% charged. And then at the moment when we drew almost 1,000 amps from that battery, the voltage was pulled down to about 8.5 volts. That's a battery load test. We loaded the battery and tested the voltage while the current was flowing. The minimum voltage that's acceptable on this test is 8.0 volts. So this battery at 8.5 passes the test. And you might recognize that when we do other battery load tests, such as using a carbon pile load tester or the min-max function on our multimeters, that 9.6 is the minimum acceptable voltage. But because this lab scope is so much faster, it captures this thin little spike right here, we have to lower that threshold, and 8.0 volts is the minimum voltage that's acceptable. Okay, the other thing that we can learn about this battery is the charge rate. You'll notice that right here we started out at 0 amps. Let me pull the ruler down here and mark off 0. started out here at 0 amps, and during cranking, the current went positive. If we zoomed in a little bit closer, you can get a closer look at what happened. Right here, the key was turned on, the starter solenoid engaged, and then the starter motor began to spin. And this was cranking right here. These are the compression strokes of the engine. And then the starter motor was turned off, and current went negative. The reason that happens is now the charging system is beginning to work. So here, current is flowing out of the battery, and then here, once the charging system starts working, current begins flowing back into the battery, and it is negative. But we want to take a look at what happens out here at 5 minutes. You'll see that this current is rising, which means it's getting closer to 0 and the battery is becoming more and more charged. That's a good sign. If this current doesn't rise, it means the battery is not accepting the charge, and it means the battery is sulfated or won't accept a charge. But if we come out here at about 5 minutes and pick a spot, we want to find out. It still is negative. You'll see it's still averaging below this 0 line, which is expected because there will be always some current flowing into the battery as long as the voltage at the generator is higher than the battery voltage. But because of all of this noise and hash, I can't determine what the actual number is, so I'm going to bring out a set of rulers and then add a measurement to find out what the actual number is. I'm going to measure the average between the rulers. And the number should be within 5 amps. So after 5 minutes of running, you should be within 5 amps of 0. It'll still be negative, but we're charging at a rate of 2.28 amps, which shows that this battery is in great condition. It's accepting the charge. It's been recharged after the draw that we put on it when we started the car. So this battery passes every test. Now let's look at the starting system. I'm going to zoom into this section again right here. And as we get closer, we'll notice that right here, this initial spike is where the key was turned on. But then right here, we have this ramp. And this is where the starter solenoid energized. And the current ramp that resulted as the current began to saturate the coil of the solenoid. Now it's different on different waveforms. Typically you'll see a little bump right here. This bump represents where the solenoid actually began to move. So this was ramping up and we got enough current that right here at this point the solenoid began to move, and then right here the contacts closed. So we can see, if we want to pull this down, we can see that the starter solenoid used approximately 46 amps. When we come to this point, we want to zoom in and look at this line. So this is a very crisp line. When the solenoid contacts engaged, they engaged once. Often what you'll see right here is they engage once and then they disengage and engage twice, and that represents bouncing or arcing solenoid contacts. So you can kind of determine the health of the solenoid right here. This is where you want to have your highest sampling rate possible, and you don't want to have any filters turned on because you want to see this line. This is actually kind of rare that we were able to turn on that solenoid with one attempt. The next thing we can look at, as we zoom out just a little bit here, are we see that these bumps represent the compression of the cylinders. But inside of here, these small bumps represent the brushes riding across this commutator segments. And they should look just like this. But I do have enough to say that they're in good shape, because if I didn't, I would see them dropping out. You can measure the distance between the top and bottom of these hash marks, and it should be within about 50 amps of each other. If you have a problem and the brushes in the starter are worn out or the commutator segments are worn out, you'll see that they drop out right here. Let me show you an example. I have another waveform here. This is a starter motor that someone was bench testing, and they were only measuring current. So you see they started out at 0 amps. Let me just zoom in and then come down and highlight a long, skinny portion of this waveform that includes everything from top to bottom that I'd like to see. And then if I have a mouse that has a scroll wheel, I can use this scroll wheel to scroll in and out. I just place my mouse over the segment that I want to zoom in on, and I scroll that wheel and it moves in and out. But now as we look at this one, when we zoom out, you can almost see the pattern here that we wanted to see. But if you zoom in closer, you'll see that it drops all the way down to 0. So some of the brushes are making contact. What we should see, we should look kind of like this. We should see this hash without all of these dropouts. During every revolution of the starter motor, it actually loses contact completely on some of the commutator segments, and it drops out to 0 amps. And then it does it again. You can see a repeating pattern here as the starter motor spins. So this starter motor probably just needs a set of brushes and nothing else. But I'll close this, and then we'll go back to our waveform that we were looking at, and you'll notice how this is 0 down here. Nothing dropped out. We had no dropouts. It was very consistent in here. Okay, now the last thing we want to do is look at the charging system. With the charging system, there are a few things that we can check out. First of all, we want to make sure that the charging voltage was in the right range. And on a car, the charging voltage should typically be between 13.5 and 15 volts. So let's come along here and take a look. And we'll see that we were at 13.64 volts at this point. So that's right within that range and everything looks good. The next thing that we can look at is we can zoom in on this line right here, and we should be able to see the alternator ripple. You see that? This ripple represents the tops of the AC waves that are alternator made. The alternator is called an alternator because it makes alternating current, but then is converted into direct current. But you'll still see that slight ripple as the voltage fluctuates just a little bit. Well, we want to make sure, as a rule of thumb, that ripple should never fluctuate more than about 250 millivolts. So let's come over here and measure the top to bottom of our ripple, just approximately, and come up and check. And we're at 145.5 millivolts. So that alternator ripple looks good. If we were having problems with the stator windings or with the diodes within the alternator, this wouldn't be consistent. We would be having a wider range on our ripple, or we would be having dropouts again, inconsistencies. But this is a very consistent and very nice looking alternator ripple. I told you that it was optional that I moved the current probe over to the alternator output wire, and then we went and turned on all of the major loads, electrical loads in the vehicle. We wanted to see what would happen to the battery voltage when we did that. So let's zoom in on this section right here. This is where we turned the loads on, and you'll see the current rose and the voltage dropped. But the voltage should be able to, especially when we raise the RPM up to about 1500 RPM, the voltage should be able to maintain or regulate itself between 13.5 and 15 volts still. So as we zoom in here again, you can kind of see that alternator ripple. But we want to take a look at this. The current that we drew roughly from when we turned on all those loads, we were drawing about 64 amps from this generator. So the generator is produced 64 amps. And at that moment when this happened, the battery voltage got pulled down to about 12.46 volts. And then right in here is where we raised the RPM, and the voltage was able to go back up to about 13.5 volts. Now the voltage regulator in this charging system should be able to increase the field current to the alternator to keep the voltage maintained between the 13.5 and 15 volt range, even while all of the loads are on. And as we look at this one's marginal. This one isn't quite maintaining, or it's very close to 13.5 volts. So it seems like it's barely able to maintain its proper voltage while the current is flowing. But that's how we load test a charging system using the lab scope too, if you wanted to have that additional information. So those are the things that we can learn about the battery, the starting system, and the charging system. I've had many instances where the car was still starting and still seemed to work fine, but there were complaints of intermittent starting or of strange noises coming from the starter motor. And that while the car appeared to start normally for us, we were able to perform this test and then zoom in and find out that there was a problem in the starter motor, that the brushes were worn out or something else was wrong. I want to show you just one more waveform here. This waveform was taken off of a vehicle. Same thing, starting and charging test, but as you look at this, here's where the solenoid turned on. There's the little bump that represents the solenoid moving. And then, once it ramped up and the starter motor began to spin, you'll see that it dropped out regularly. So again, here's a starter motor that's working. You'll see the compression bumps when you zoom out. It's working, but it keeps dropping all the way down to 0, indicating that we have worn brushes in the starter motor. So you can learn an awful lot about the starting system, the charging system, and the battery from this waveform. So I would encourage you to go capture this type of a waveform and practice analyzing it yourself so that you can know what to expect to see from a properly functioning system.